Welcome to the presentation. We proposed an approach to classify date fruits using deep learning techniques. Our objective was to classify date fruits into three classes: hard, soft, and semi-hard, collected in Oman. Our dataset consisted of 600 images per class for a total of 1,800. In general, a solution can involve the selection of hardware, which in our case, the selection was a camera. If possible, we wanted to select a sensor aid, like control lightning, to avoid undesired light reflections from the fruit. Also, we explored image preprocessing to help on the classification part. In machine learning, we required extraction of features. Once the features are extracted, we can perform feature selection in order to select the ones that will lead to a good classification accuracy. In supervised training, we have information about the classes given by an expert, with the inputs labeled by the expert and the inputs coming from the features. We can train a classifier. For example, we can use a support vector machine to obtain our final decisions. In deep learning, the features are extracted automatically with a convolutional neural network, avoiding with this some of the steps mentioned before. Unfortunately, the total number of examples that we have available is 1,800, which usually is not enough for training a CNN. In order to generate more data and be able to use deep learning, we propose the use of Generative Adversarial Networks, or GANs. Briefly, the general steps taken by a GAN network are the following. Noise is fed into the generator, and because the generator hasn't been trained yet, the output looks like noise in the beginning. In a second step, training data and the output of the generator is sent to the discriminator, which identifies real fake images. The output of the discriminator at the beginning is not accurate, but will improve. In step 3, the output of the discriminator can be fed back to the generator, which can use this information to update parameters and attempt to improve on the accuracy. GANs have been used to generate images of people, like the ones you see with incredible results. Our original images were gray level ones, and we preprocessed them using pseudocoloring. This based on selecting color maps other than the gray level value one. By doing this, we can see that training accuracy improves depending on which color map is used, and as you can see, it is the jet color map that offers the best result, and that is the one we used. We separated our data into test and training images. 300 test images were randomly chosen, 100 per class, and the rest were to be augmented using GANs. So that part of the GAN conforms the data augmentation part. So we generated 1,000 extra images per class this way. The figure shows examples of these GAN-generated images. We choose a DenseNet CNN that connects each layer to every other layer in a feed-forward manner. The feature maps of all preceding layers are used as inputs for each layer, and its own feature maps are used as inputs into all subsequent layers. DenseNets have several compelling advantages. They alleviate the vanishing gradient problem, strengthen feature propagation, encourage feature reuse, and substantially reduce the number of parameters. The results obtained using a three-class classifier based on the DenseNet model are shown in the confusion matrix, where we can see the excellent accuracies obtained, but not necessarily for the semi-hard cases, as we can see an accuracy of only 89%. We note also that there is one misclassification of a hard date, which is right there. Training a two-class DenseNet for the hard and soft cases only yields the following confusion matrix. We can see here how we can achieve perfect classification. Once we train both networks, we use the test set to generate scores in the form of probabilities that can be seen as how confident the networks are of the classifications. The idea then is to combine these probabilities using an expert system. to improve on the three-class classified results. In red, in that plot, we can see the classification done by the two-class classifier for the hard cases. High probabilities are seen except for two images, this one and this one, but both are higher than 0.5. In blue, we can see the classification done by the three-class classifier. Note how there is one misclassification as seen as the confusion matrix before, this one here, with a low probability hinting the similarity of the semi-hard images with the hard ones, and even some of the semi-hard images look like soft ones. Here are the 100 images probabilities corresponding to the soft cases, and once again we can see that the two-class classifier has high probabilities except for a few cases, but still greater than 0.5. As expected, the three-class classifier also achieved 100% accuracy with high probabilities for most cases. For the semi-hard cases, the two-class classifier has no option but to assign them as soft or hard only, and the three-class classifier, as expected, has the semi-class outcome but produces misclassifications. A critical value to test will be 0.5. Defining a threshold with this value, we can see that if both probabilities are higher, we can select the output from the three-class classifier, knowing that there will be only one mistake. For the semi-hard cases, values below 0.5 are misclassifications for the three-class classifier. Everything above seems to be correctly assessed. There are image outputs, such as the ones highlighted with the arrow, where both classifiers wrongly select a hard case, but with very low probability. Here is another case. We can then choose a semi-hard output when this scenario happens. The result from both classifiers then can yield better accuracies. This is done with an expert system, as shown there. The block diagram shows the implementation of this, where we can see that if the conditions are not met, we simply select the classifier with higher probability, which is happening here at the end. The final result is shown in the confusion matrix, where the accuracy of 96% using the three-class classifier is improved to 99.7% using the expert system. More information can be found on the references found in the description. Thank you.